I don't know why I'm here, but there's one thing I do know. It seems that I need to solve this problem. Still, this is a strange equation. This looks like differentiation with respect to x, but it's being treated as if d by dx were a number. And somehow the result of the calculation is the exponential function. This makes absolutely no sense.
Zundamon, you seem to be having trouble.
What? Who are you?
There's no need for introductions. More importantly, this equation isn't complete yet. You need to replace d by dx with a slightly special form of differentiation. For now, replace d by dx with an uppercase D, and try proceeding with the calculation.
What do you mean? Wait a minute, I need to talk to you. She left. Oh well, let's just follow what she said. I was supposed to replace d by dx with an uppercase D, right? Then it looks something like this. What do I do from here? I think she told me to proceed with the calculation. I'm not sure, but for now, since it's hard to handle in fraction form, I'll eliminate the denominator. Multiplying both sides by d minus 1 makes the left-hand side 1, and transforms the right-hand side like this. Okay, let's expand the right-hand side. Is this right? I see. So d to the x it seems to be equal to e to the x plus 1.
Looks like you're making progress.
You're the one from earlier.
D is slightly different from the usual concept of differentiation. Are you starting to understand?
Now that you mention it. Normally when you differentiate e to the x, the result should also be e to the x. But there's an extra plus 1 here. What exactly is this?
Sounds good. Please use this.
This seems like a tricky one. I need a proper explanation.
You're kinda troublesome.
Metan, I'm glad you're safe. By the way, where did she go? Never mind.
From here on, things will get quite advanced. If there's anything you don't understand, try reviewing it a few times.
What do you mean?
Alright, let's begin the explanation. Here we assume that the variable x is non-negative. Also, the functions we will discuss from here on are basically assumed to be continuous functions defined for x non-negative.
Continuous functions. So just to keep it simple, functions with nice properties, right?
Something like that. Now for two functions f and g, we define a new function f star g. This is called the convolution of f and g. Here we multiply f of x minus t by g of t, and integrate the result with respect to t from 0 to x. Since we're integrating over t, the right-hand side is a function of x. The range of integration depends on the context, but here we define it as from 0 to x.
I kinda get it, but not really. So what exactly is convolution?
Convolution appears in many areas of mathematics, but it's hard to explain in just one sentence. For now, you can think of it as a method to create a new function from two functions.
I see.
Convolution shares several properties with ordinary multiplication. For example, the commutative law means that the convolution of f and g is the same as the convolution of g and f. Next, the associative law states that when computing the convolution of three functions, it doesn't matter which two functions you convolve first, the result remains the same. Additionally, the distributive law holds as well. That means, when convolving with the sum of functions, you can first convolve each function separately, and then sum the results.
I see. Convolution resembles ordinary multiplication. Then we need to prove these formulas.
No, we don't have time for that. For now, let's just accept these formulas, and move on.
Really?
Anyway, let me write down the definition of convolution.
Oh, I've seen this before. By the way, what was I trying to do again? Oh right. Some kind of differentiation-like thing appeared as the problem. So how does this thing called convolution relate to differentiation?
No need to rush. It might seem like a detour, but to understand differentiation, let's first think about integration.
Thinking about integration first. I don't really get it, but let's just keep going.
Now, we consider the following convolution.
The convolution of 1 and f? What is this 1?
Here we are using a constant function that is identically equal to 1, and writing it simply as 1.
Oh, I see.
Also note that the variable x is often omitted. Now, what happens when we compute this convolution?
This is a tough question. For now, let's calculate it using the definition of convolution. The convolution of f and g is defined like this, right? Since we're computing the convolution of 1 and f here, the f of x minus t part becomes 1, and the g of t part becomes f of t? So in other words, it means integrating f of t from 0 to x.
That looks correct. So in this case, 1 is playing the role of integrating f through convolution. To put it another way, if we define I as 1, then the convolution of I and f becomes the integral of f, starting from 0. Thus this can be written as f of x minus f of 0. Here uppercase f is the antiderivative of lowercase f. In other words, differentiating uppercase f gives lowercase f.
Oh yeah, I think I remember that. So I represents integration through convolution. But normally, when considering an indefinite integral, I feel like something like this always appears.
You're talking about the constant of integration. When dealing with an indefinite integral, there's always some ambiguity due to the arbitrary constant. But in this case, integration with I does not have that ambiguity. That's an important point.
Oh, I see.
Now let's move on to differentiation.
I've been waiting for this.
First, let's recall the relationship between differentiation and integration.
The relationship between differentiation and integration, if I remember correctly, in the case of a single variable, integration is considered the inverse operation of differentiation.
That's exactly right. Similarly, let's think about the relationship between D and I.
What's this? The relationship between D and I? Alright, let's think this through calmly. First, I is what we defined earlier as representing integration. Its actual definition was the constant function 1, right?
Yes, exactly.
And then this D here, since it corresponds to I, it must be something like differentiation?
That's right, so we define D as the inverse of I.
This is really interesting. So this D is the one that appeared in today's problem, meaning it's the true form of that differentiation-like thing?
I'm not entirely sure about that yet.
Really? Oh well, never mind. Let's just try it out. Now let's think about the inverse of I. What do you mean by the inverse of I?
Let's take it step by step. Before we discuss the inverse of I, let's prepare some groundwork. First, let's consider a function called delta. If f is any continuous function, then the convolution of delta and f equals f. In other words, we assume that convolving with delta leaves f unchanged.
Wow, that's kind of interesting. In normal arithmetic, multiplying any number by 1 doesn't change the number. So in convolution, delta plays the same role as 1 does in ordinary multiplication.
That seems like a good way to understand it.
But does such a delta actually exist?
Without that, actually, such a delta does not exist.
What, really?
To be precise, delta corresponds to something called the Dirac delta function, but it is not a function in the usual sense. However, explaining this rigorously would take too much time. For now, let's just assume that such a delta exists and move forward.
Got it. It feels kinda weird.
Alright, now we're ready. We define D as the inverse of I. That means this. Even the existence of this D is not guaranteed, but let's not worry about that for now.
The convolution of D and I results in delta. So does this mean that D is the inverse of I? I'm not sure I understand what you're saying.
Alright then, try taking the convolution of this with f.
Taking the convolution with f. So in other words, first we can write the convolution of D star I and f like this. Next, the convolution of delta and f equals f, since convolving with delta doesn't change the function. Finally, the convolution of I star D and f can be written like this.
Yes, this means if you integrate f first and then differentiate, you get back f. And if you differentiate f first and then integrate, you also get f. That's how we can interpret this.
Oh, I see. But when you differentiate first and then integrate, does it really go back to the original function? Oh well, whatever. Now we just need to check if the differentiation-like operator in the problem matches this D. But how do we do that?
Zundamon, look at that.
What is it? What is this? This looks like a really complicated equation.
This is very interesting. If f is differentiable, then the convolution of d and f can apparently be expressed in this way.
Oh really? F prime looks like a normal derivative. Since d corresponds to differentiation, we can say that d star f corresponds to the derivative of f. So it makes sense for f prime to appear here. But what is this f of 0 delta? Something extra seems to be attached here.
It's a bit strange, isn't it? Maybe if we prove this formula, we'll understand it better. If we assume that the right-hand side represents the result of some differentiation-like operation, let's check if integrating the right-hand side brings us back to the original function. Of course, when we say integration here, we mean computing the convolution with I. The result should return to f.
Let's try it. First, using the distributive law, we expand the expression like this. Alright, let's go through it step by step. First, this I star f prime term represents the integration of f prime. Next, in this convolution term, let's factor out f of 0.
Since convolution is originally defined using integration, the constant can be factored out.
Yeah, that makes sense. Now if we integrate f prime, we get back f. Note that the integration range is from 0 to x. Next, since convolving with delta doesn't change the function, this just becomes f of 0i. What do we do from here?
Wait, what was I originally again?
Originally I was defined as the constant function 1. Oh, I see. So the result is just f of x?
That looks good. So if we take the convolution of this mysterious expression with I, we see that the result returns to f. We've gotten pretty close to the intended formula.
Really? But what should we do next? Okay. I want to get the form of d star f. So let's multiply both sides by d. Then d star f appears here.
Brilliant, Zundamon. Since we originally defined d as the inverse of I, d star cancels out. And with that, the formula is proven.
Oh, so that's how it works? Well, we did prove it, but that was a pretty unusual proof. Still, what exactly is f of 0 delta? It feels like this term is what makes the proof work.
That's an interesting point. Take a look at this equation for a moment. Here, f of 0 delta retains the initial value information of f of 0. That's how we can interpret it.
What do you mean by initial value?
Normally, when you differentiate a function, you lose its initial value information. So if you integrate afterward, a constant of integration appears. Since the constant of integration is arbitrary, you can't fully recover the original function. But here the differentiation process retains the initial value, so when you integrate again, you can completely recover the original function.
I have no idea what you're talking about.
It's a pretty tricky concept, so feel free to ignore it if it's too confusing. Anyway, now that we've proven the formula for differentiating f with d, let's look at an example. Zundamon, what happens when f is an exponential function?
This is the case where f is e to the alpha x, right? If we apply the formula, the derivative of f is the derivative of e to the alpha x. And f of 0 is e to the alpha 0. Now then, when we differentiate e to the alpha x, alpha appears as a coefficient. And since e to the 0 is 1, this part just becomes delta.
That's right. Since e to the alpha x appears in two places, let's combine them into one.
Alright then, for now, let's move e to the alpha x to the left-hand side. Well, what should I do with this? The star here represents convolution, while alpha and e to the alpha x are just multiplied normally, so we can't factor out e to the alpha x.
Oh, that's true. Then, how about doing this?
What delta appeared? Oh, I see. Since delta in convolution acts like 1 in normal multiplication, this way we can factor out e to the alpha x.
That's exactly right. Now this might be an abusive notation, but let's consider delta as playing the role of 1 in normal multiplication, and rewrite the equation in this simpler form. Additionally, the convolution symbol star is also omitted.
This is getting really complicated, but at least it looks simpler.
Now let's formally divide both sides by d minus alpha. Then we get this equation. Be careful. the left-hand side and right-hand side have swapped places.
What does 1 over d minus alpha even mean?
If we were to approach this rigorously, it would become quite a difficult topic. Roughly speaking, if we take a close look at this equation, applying d minus alpha to e to the alpha x results in 1. So just like e to the alpha x, 1 over d minus alpha is the function that results in 1, when d minus alpha is applied to it. As a simple interpretation, this is one way to think about it.
Oh, so that's how you think about it.
In particular, if we consider the case where alpha equals 1, we obtain the following equation.
Ah, this is it! We finally obtained the equation that appeared in the problem. It's a simple equation, but it took quite a long time to get here. By the way, what is this equation actually useful for?
Well, that's a natural question. Let's take a look at an example. We consider the following differential equation. Let y be a function of x, and suppose that the second derivative of y minus y itself is 0.
In other words, taking the second derivative brings it back to itself.
The term differential equation might sound difficult, but essentially we just need to find a function y that satisfies this condition. Here we set y of 0 equals 0, and y prime of 0 equals 1. Now let's write down the formula we proved earlier.
The convolution symbol star is missing, and it seems that delta is also omitted.
It's written in a simplified form with some symbols omitted, but let's not worry about it for now and move forward. A differential equation usually involves regular differentiation, but let's try rewriting it using d.
I see. Alright, first let's compute dy. Then we get this result. Using the condition y of 0 equals 0 here, only y prime remains.
So we've confirmed that dy is equal to y prime?
That's right. Next, let's compute d squared y. Here, d squared corresponds to the second derivative, meaning we apply d to dy. Since we showed earlier that dy is equal to y prime, we just need to compute dy prime. Now applying our formula again, if we replace f with y prime, then f prime becomes y double prime, and f of 0 becomes y prime of 0. Using the condition y prime of 0 equals 1 here, we get y double prime plus 1 as the result.
That turned out to be a simple result.
If we write only the result, it looks like this. So, what should we do from here?
We were supposed to rewrite the differential equation using d, right?
Oh yeah, that's right. To bring it closer to the form of the original differential equation, let's subtract y from both sides. The left-hand side becomes like this, and the right-hand side looks like this. Here, as if we could apply the distributive law, let's rewrite the left-hand side in this way. On the right-hand side, the form of the differential equation appears as is. So in the end, only 1 remains.
We finally made it this far. Now let's divide both sides by d squared minus 1.
Well, let's give it a try. Dividing both sides by d squared minus 1, we obtain this equation. In other words, y is now expressed in terms of d. No way. The left-hand side is a function of x, but on the right-hand side, the denominator contains d.
It's a strange feeling, isn't it? Okay, let's try factoring d squared minus 1.
What? Are we really allowed to do that?
That's up to you.
Now if we factor d squared minus 1, it becomes like this. This looks like it can be decomposed into partial fractions. Yes, let's rewrite the numerator 1 like this. Here we've arranged it so that the d's cancel out. Since 1 plus 1 equals 2, multiplying the denominator by 2 ensures that it matches the original equation. And this part becomes 1 over d minus 1. And this part becomes 1 over d plus 1.
This is the form 1 over d minus alpha appears.
Oh, you're right. That means, if we forcibly apply this formula, first 1 over d minus 1 becomes e to the x, and 1 over d plus 1 becomes e to the negative x. I don't really know what I'm doing anymore, but at least we got the answer.
Amazing, Zundamon. this is in fact a solution to the given differential equation. Since this is a simple example, solving it normally might be faster. If you've ever used the Laplace transform to solve differential equations, this method might look somewhat familiar to you.
I don't really recognize it.
This method is an example of operational calculus, where differentiation is treated algebraically. In particular, this approach was developed by the mathematician Jan Mikusiński.
No matter how many times I look at them, these equations remain a mystery.
Doing it rigorously would be quite difficult, so we had to sacrifice some rigor along the way, but I hope you got a sense of the idea that convolution can be extended.
Well, since we were able to use this formula to solve the differential equation, I feel like I've grasped something amazing.
Well then, take care everyone.
See you later.